There are two ways of approaching the verification problem, if you will. There's a technology-focused approach and a mission-focused approach. And both of them, I think, are very important. And in many ways, the CVT, at least that's the way I see it, tries to combine both. So it's a hybrid approach. And I think there are unique opportunities for synergisms in this area. The, research area 1, the policy research thrust, really emphasizes, of course, the treaty enabling approach. So we start with the treaties, and I'll have them on the next slide. There are a bunch of them. And then we try and look at what's the problem that we're trying to solve, where are the gaps, where are the challenges, and then see what everyone's doing and how this fits into the big picture. Here's a list, and you can probably, this was also in Sarah's talk. There's a handful of treaties, and here are the 4 most important ones: NPT, CTBT, FMCT, and what I call next generation nuclear disarmament treaties. So, and this is, I guess, the mission for the next few years. Certainly, it's kind of hard to imagine a number of new treaties that are kind of not captured here on the slide, but who knows? They may one day be on the horizon. So what I'm trying to do is split this talk up into these different areas, and I start with CTBT, and we'll lump, if you will, the FMCT with the FMCT with the NPT, because they are very similar in terms of the verification challenges. So the CTBT, as you know, it's a funny treaty, has a tragic history, if you will. It's been around for almost 20 years now, and it has a very detailed verification protocol. And since we had so much time to kind of think about the CTBT and how to verify it, there have been many studies that looked into this. And I just have 3 here on the screen. There are 2 National Academy studies in 2002, 2012, and there's a recent book on verification of the CTBT. The bottom line is, and what is really amazing, compared to 1996, when we negotiated the treaty, the verification capabilities have improved tremendously by an order or maybe 2 orders of magnitude. Back then, the idea was to detect explosions on the order of 1 kiloton, and as Paul and others will emphasize, we're now down in the range of where we talk tons of yield, which is quite impressive. So what are then the gaps and challenges? We can always do better. So there are kind of 2 main technical approaches to CTBT verification. The first one are the waveform-based techniques. So that's seismic, it's infrasound, and is hydroacoustic. We focus in the CVT mostly on seismic and infrasound. And we have various groups working on this, most importantly here, Paul Richards in Columbia and Milton Garces in Hawaii with their teams. And the challenge here is to detect very low yield explosions. And if you do detect, or low yield events, I should say, and if you do detect them, discriminate them against other sources. And I guess there will be more coming up today and tomorrow. There have been quite some advances in improved event location and identification especially also through integrating infrasound with seismic monitoring techniques. The second part of the big and very different kind of a technology, of course, is radionuclide signatures, mostly xenon isotopes. Here again, we have many groups working on this. This is kind of a smoking gun, of course. If you find certain radioisotopes, you can be sure that a certain event was nuclear in nature, but you won't always find it. You do have explosions, or you can have explosions that will not leak xenon isotopes. But again, here the main challenges are advanced detector technologies, higher energy resolution, lower minimum detectable concentrations. Avi Forsoni and his team will be presenting on this. And then second, state-of-the-art atmospheric transport models, moving both forward or backward and forward, in the sense that you would try to find the origin, the location, and the time of release, and then also forward when you try to catch the plume and try to figure out where it's going and where you should make the next measurements. So I'll have, two very quick examples just to highlight this, and I don't want to steal people's thunder, so this is just supposed to be a teaser here. This is Paul Richards' work, and he'll be presenting later, who is developing algorithms and techniques to detect very small, or to distinguish very small nuclear explosions from very weak earthquakes. And he'll give us the latest updates on this. So I just leave it at that. Second, this is some work that we've been working on in Princeton. Michael Schöppner is going to present this tomorrow. And this is actually also a movie, which doesn't work in this PDF. But what he's doing is atmospheric transport models to kind of identify gaps and gaps in the radioisotope network, and essentially figure out, if you expanded the network of detectors, where would be the best locations to kind of find, close these gaps, as you can see here, for example, in South America. John Lee, I guess, is also working with atmospheric transport models. So there will be a presentation about this tomorrow. So this is on the on the CTBT, on the FMCT. And as I mentioned, I merged this here with the NPT, and of course the NPT has been around for many years, and we know how to verify. There hasn't been a lot of progress on the FMCT, of course. It's still stuck at the CD. There has been some progress. There was a group of government experts that convened over the last year. We have seen a draft treaty that France tabled, so that's something. But there's a final report that also emphasizes or kind of shows where agreements and disagreements are between those who are involved in the discussions. And it goes as far as not agreeing, or there's no consensus on what fissile materials are. And should the treaty, for example, ban the production of any HU for weapons purposes, or should, for weapons purposes certainly, but where should the enrichment limit be? There's no agreement, and this could have implications for how we would actually verify the treaty. But that said, there hasn't been a lot of progress otherwise. The most important observation, in my view, when we talk about how to verify the FMCT, is that it really is very similar to NPT verification in many ways. There is already an FMCT for non-weapon states, which is the NPT. So it's obvious that IAEA safeguards techniques will play, or could play, a very important role in verifying the FMCT. There are differences, and I will say a few words about them in a second. And then there are also challenges like the one shown here on the right. This is a picture from a Russian enrichment plant, the biggest enrichment plant in the world, about 15 million SWU per year. And of course, no IAEA inspector has ever been there, and it's kind of unclear how you would be able to kind of retrofit IAEA kind of type safeguards into such a facility, which on top of that produced HU in the past. So you couldn't really do swipe sampling and other techniques. So that's kind of an open question, how we would kind of capture these large facilities. There are other cases where in India, Pakistan, for example, it may make more sense to just shut down some smaller facilities instead of trying to convert them to civilian purposes if these countries sign the FMCT. Examples, again, this is, as Sarah actually mentioned this already in her presentation for FMCT and NPT, real-time characterization of nuclear materials. Many groups working on this as part of the CBT, and I apologize if I forgot names that should be on this slide. So approach me and let me know to add you. So determine mass, enrichment, and location of nuclear materials, and then especially for FMCT, also the idea of perhaps combining these instruments with information barriers. So we would be making measurements, we may be making measurements at facilities in weapon states where certain types of information may not be or should not be revealed. So combining instruments with information barriers could be a valuable kind of addition, and we're looking into that. Then second, the elephant in the room, and that's really also an NPT problem, of course, is the ability to detect clandestine facilities and activities. Again, we have many people working on this. I think Paul Wilson's work in Wisconsin with cyclists is relevant here. Detect fuel cycle anomalies, data analytics. We have several groups working on this. But then also emission source terms and atmospheric transport modeling to understand the signatures from these facilities, if they existed, better than we can today. Examples, this is work done in Sarah's group. I think Angela is going to present this tomorrow, and I think you moved from liquid scintillators to solid scintillators and have real-time data processing capabilities and can now discriminate neutrons from gammas and get, for example, mass in real time. So that's one development, and I think it's going to be relevant. Second, this is Igor Jovanovic's group at Penn State University, laser-induced breakdown spectroscopy. They are able to distinguish HEU from low-enriched or natural uranium with LIPS. And again, this would be particularly valuable if combined with an information barrier, for example, to confirm, for example, in a facility that no U of 6 is present. If you could kind of confirm there's uranium, but you can't find fluorine isotopes or elements at the same time. So that's, I think, exciting work, and it would be very valuable for FMCT applications. And then finally, again, this is work that we've been working on in Princeton. Michael Schöppner, Mark Walker. Once you have your atmospheric transport model, you can do xenon, but you can also do krypton, I guess. And so here shown here on this map, the variations in the global krypton background. And I think you get the basic idea. There's much more variation in the north, where the declared reprocessing plants are. And what we're trying to kind of figure out, and we had a paper at INMM, and there's more coming, is how difficult is it then to detect clandestine or undeclared facilities in different regions of the world, and how many samples would you have to take, random samples, if you wanted to find one, and are there kind of smart ways of doing this? So that's kind of also, I think, work that hopefully can inform the technical work that others are doing in terms of detector development and so on. And then finally, on the next generation nuclear disarmament treaties, here, and again, Sarah had a number or a few slides on this topic. Of course, there are no new developments on the policy area, really, because the relations with Russia are so great right now. But again, this is maybe the time to do the technical work. And here, really, everything, everything related to verifying these treaties will be about protecting sensitive information. So can we somehow reinvent measurement techniques and measurement approaches so that information is protected and perhaps never actually measured? So this is kind of the big picture, I think, problem. I tried to break it up into two different boxes here, but it's somewhat arbitrary, perhaps. So protecting sensitive information, Claire Sullivan, Dave Weehee, have been mentioned with their work on inherent information barriers that are kind of removing information on the kind of on the software and hardware side, kind of inherently. And I'll have a sample and an example in a second. I think more conceptually, it's also important to look at verification approaches that are minimally intrusive. Can we somehow figure out how to do it in a way that it's kind of compatible with the environment we're in? And then it's a final note. We eventually have to confirm numerical limits on, say, nuclear weapons or warheads. Are there new ways of tagging warheads or other treaty accountable items in a way that it's kind of acceptable by the host? Then second big group, but it's kind of related, of course, is confirming the authenticity of nuclear warheads without revealing design information. MIT is pursuing the NRF approach that was mentioned, and we in Princeton, we do neutron radiography and fission signatures, kind of using a zero-knowledge approach, and I think we have 2 talks on this tomorrow, so I won't even mention it here anymore. 2 examples before I kind of wrap up. This is Dave Weehe's work, and I'm not sure you can actually see very much. But essentially the idea is, and he'll present this, you have an original high-resolution spectrum shown here on the left, and you want to remove the information kind of downstream, or I should say upstream, as soon as possible, so that you only measure what I called here a featureless spectrum. But then I need to find a better term of art here, and maybe you have one, that only preserves the one area of the spectrum that you are allowed to see and you're interested in. So the rest of the data is actually never really processed. And I think Claire Sullivan is doing related work. Let me skip over this. And then just mention one final project that also we proposed in Princeton, and we're now kind of just launching, is a warhead dismantlement facility and managed access simulator. Trying to can we build and kind of practice and explore verification approaches in VR, so we're working on this. We have a PhD student who just joined our program that will be, I think, her main project, and she's done some work on this already. And so, for example, what we just actually acquired, and I can just put myself on the spot and say next year we could maybe demo it here when we're further along. We acquired a full motion VR system. The idea is to actually implement real-time radiation fields. So that's the longer-term kind of physics aspect of it, but in a way so that you have host-inspector interactions in virtual reality, and you can try out things that UK Norway is doing in real life. We think that there is a case to be made that might be easier or cheaper, if you will, to do in VR, and also actually make possible collaborations across the country or perhaps even internationally. So we will have a local system that will be more, fancy, if you will. But eventually, I think the idea is to move to a mobile system where you have this Google Cardboard, essentially technology, and you can just, experience the environment in, kind of wherever you are. I think technology-wise, we're still a generation or 2 behind, so we need an iPhone 7 or iPhone 8. To pull this off, but I'm sure by the time CVT kind of moves forward, we get there. That's what I had, and I guess I am out of time. We will have we'll have a small workshop on Policy Research Area 1, jointly organized with MIT in December. We're kind of trying to brainstorm more about what we should be working on. But that's about it. I don't want to steal Frank's time here. Thanks again to everyone, especially, of course, the CVT and the NNSA for making this possible.
So the outcomes of our consortium, so in 5 years, we expect to have a very deep understanding of the policies and technical aspects of